Okay, this is the key to the exam. 3. PCC is a mild oxidant, meaning it's not gonna oxidize further than aldehyde or ketone. We see this as secondary alcohol. How do I know that? Because this carbon is bonded to two others. Secondary alcohols must always be oxidized to a ketone. This is Jones. That's a strong oxidant. Aldehydes will be oxidized further to carboxylic acid. This is a secondary alcohol, still ketone. PCC is mild. I see that this is a primary alcohol, so it should be oxidized to aldehyde and stops at the aldehyde, which is that. This is Jones, strong oxidizing agent. This is tertiary. Tertiary never oxidizes. No reaction. This is Jones. This is primary. It would go through formation of that aldehyde, but does not stop there. Goes all the way to carboxylic acid, because again, that's a strong oxidant. Okay. HCl with alcohols, usually SN1. That's a tertiary alcohol. SN1 goes through formation of a carbocation intermediate. OH is not a good leaving group, so the first step is protonation. Pick up the hydrogen from HCl. You want this leaving as water, not as OH. OH will leave to give you a strong base. So after protonation, in the mechanism, the water falls off. You get the phenol ring, which is the benzene. You get a carbocation, and you get the 5-membered ring right there. Remember, water fell out here, Cl fell out there. So the Cl, if you have excess of HCl, the Cl should be attacking that plus sign, which is substitution. So the OH is now replaced with Cl. Okay, this is a tertiary carbocation. No need for rearrangement. Here, this is E1. This was SN1. This will be E1 because I see now the acid of choice is bulky, not like HCl, which is small, where Cl minus will come back to attack. This one will lose a hydrogen, yes, but it will not come back to attack. So again, same step. E1 and SN1 go through formation of a carbocation to give you the carbocation intermediate. So you get your water activated to leave after protonation. That's just an acid. This will fall off, and pH again is the ring. I'm just using it as shortcut. pH is right there. You have a 5-membered ring here, and the water fell off, so you get H2O. We are thinking E1. There's no beta hydrogen here, there's no beta hydrogen here, but it's here. So you will take out that hydrogen and make a double bond. So the answer should be A. UPAC naming, prioritize position of the alcohol. So this happens to be a cyclohexanol. Hexanol with a methyl group on the 3rd carbon. So it's 3-methyl cyclohexanol. Here's the methyl group. Again, prioritize the alcohol. 4, 5, 6, 7, 8. Looks like this is an octanol with the alcohol on the 2nd carbon. So the name for this, given that this is a substituent, would be 7-methyl. Okay. 2, position of the alcohol, octanol. I would have called it octan 2-ol. Okay, of course that's a phenol, and this is cyclo. Pent, there's 5 carbons, not pentane. Replace the E with OL. I see an OH here. There's a sharp peak there, but there's an OH here that I see. That OH belongs to OH will belong to an alcohol or carboxylic acid, most likely an alcohol. And let's see what we have here. I have the overtones. This suggests that I have a phenyl ring. Okay, either those or these are the overtones, regardless. I think this is the most likely because it's about 2200. Don't know what that sharp peak is, but the best matching one, given that there's no carbonyl, yet we have, see right here, this peak is above 3000. That must be an sp2ch. So this would have been best phenol. Okay. If the carbonyl was there, let me see. We see 1, 11, 12, 13, 14, 15, 16. 11, 12, 13, 14, 15, 16. Okay, I have no carbonyl at 1700, so it cannot be carboxylic acid. Plus, this would have been so broad, would have started from somewhere here, broad. So best choice is B. Actually, looking closely, should be B. And then this one, best choice would be let's see, our ketone. Best choice here, this would be a ketone. Actually, this should be that, because I see I have something at 1700. There's nothing else I see. There's no broad here, so it cannot be that, cannot be that, and it cannot be that. Now this is extremely broad. I see it's so broad. At the same time, I have a carbonyl. This could be an OH. So the best choice is that. You see we have some sort of overtones there suggesting the aromatic ring. Okay, so for this one, 1, 2, 3, 4, 5, 6, 7. So this n equals to 6, 2, 3, 4. N equals to 4. Because n equals to 3 here, because m equals to 4. Remember, the formula is multiplicity is n plus 1. N is number of neighboring hydrogens. And then this one, if m equals to 3, n equals to 2 neighboring hydrogens. And this, m equals to 2, so n equals to 1. So I'm looking for a molecule that matches this number of neighboring hydrogens. And looking at the chemical shift, which these hydrogens are sitting on carbons next to our electron withdrawing group. So let's see. Who is this? So most likely it's gonna be, see I have n equals to 6. If I draw this hydrogen here, it's bordered by 3. And also these CH3s, they have only one neighbor, so n equals to 1. So already those peaks are matching. And then this hydrogen is sitting on a carbon next to an oxygen, so it shows up so far. If n equals to 6, definitely m will be equal to 7, which are those single strokes I counted. And then this CH2 most likely is gonna be that, and you can see that its neighboring hydrogens are 3, and those 3 have a neighboring hydrogens 2. So that's the perfect molecule. So I see a singlet. I look here to see who has a singlet. This has no singlet in there because all these carbons have neighboring carbons with hydrogens. This is possible because that's a methyl group, and because it's bonded to an oxygen, should show up around here. This is most likely. Here there is no singlet. All these hydrogens have neighbors. They will be split. The signals will be split. Cannot be this because there's no aromatic hydrogens. even though this will show up as a singlet, but aromatic hydrogens are missing, so that's the best choice. For this one, I have aromatic hydrogens without thinking. That's the only aromatic molecule, and of course this has n equals to 0. We don't count this hydrogen as a neighbor, so m equals to 1 because we say m equals to n plus 1. These two hydrogens are those. The rest of the hydrogens on the ring are these ones, but they're gonna be aromatic. Okay. Step growth, most likely you have condensation, and that's how we make esters. You must have joined here, joined there. This piece would have been a monomer. 1 2 3 4 5 6 1 2 3 4 5 6. That's a monomer, and then the other side, if you cut here, this must have been an acid. I told you esters are made when acids and alcohols combine, losing water. That is step growth. So that's the answer. Isotactic and syndiotactic. This should be the iso, this will be the syndio, and they are alternating like that, but this one they're on the same side. This involves again loss of small water molecules, so it has to be step growth. That's a polyamide, so it's not a polyurethane, it's a polyamide because the amide functional group has this shape. Okay, carbonyl to a nitrogen. This is a polyester, correct, because that's an ester group. So this is true and this is false. That's it.